So next, we want to look into axial member again, but then the formulation wise, we are looking into how we incorporate the shape function that we have learned, okay, then in towards this particular so-called problems. Okay, we have learned how an axial member being formulated. Okay, it could be direct formulations, right? And also it could be, we can use the energy methods, okay, and uh, the minimum total potential energy methods to formulate set problems when you have a member undergoing axial loadings. Okay, so we would want to see we have a shape function coming in. At the end, you will see that you will see it is actually the same lah. You will actually come out with that formulation, the shape. What we call this shape function. You will also lead us to what we call the stiffness matrix, elemental stiffness matrix. Then we have this load matrix coming into play. Then you'll give us this KU equals to F also, right? So let's have a look on this. Right, so axial member. So it could be steel columns commonly used to support loads from various floors of a multi-story buildings. Okay, you can relate to what we call steel columns, something similar like that. So the loading from the floor, what we cause vertical displacement of various point of the columns. So here we are saying that you in these particular types of members, I mean, or what we call these particular types of cases, then you have these axial loads, okay, excite or what we call applied into that particular member, then probably cause here is talking about loading in, or what we call displacement in axially due to that particular load. Okay, so it's we have to assume that it's a central loading, axial central loading. The deflection profile represent the vertical, not lateral. So in that case, if you have a loads, okay, applying from here axially, okay, in these two cases, let's say this is what we call steel columns, okay, from the floor itself, okay, different floors, okay, multi-stories, then you have this loading. Of course, this particular point, we know that it is fixed, okay, you have zero deformation or deflection, so it is zero at here. Then towards the load itself, you basically undergoing larger deflections. Okay, so here we'll have a larger deflection with the scale of this scale. It's not lateral, it's actually vertical. But how to show you here the profile of the deflections. So you will see that here particularly will be higher. Okay, you'll see that this U will go higher at this particular point. Then slowly to this particular fixed point at the bottoms will be zero at here. So in actual profile will be, of course, something similar like this. But if you're using linear approximations, linear elements, then what we call, then we will have these straight lines. Okay, you see the approximations. Basically, want to have a look on how it will happens in this case, because this is a linear problems, right? F equals to k delta x itself. Then this linear element itself, the approximation of linear elements, so you will see that it is particularly, this is still close in a very near to the load itself. Is still very close compared to the actuals. The approximation is close, but then the approximation in very near to the beginning. I mean, at the bottom here will be if you are using linear, then probably it is the approximation is a little bit far away. Have a big difference in this case. So probably you can increase more, again, you can increase more nodes or increase the elements, okay, or you can increase higher orders in this case, okay. So we look into this, okay, how probably we can make use of the shape function that we have determined to formulate these problems, and how we can approximate, okay, any what we call deformations or deflection at any point of position of these particular columns. So this is what we have discussed or learned just now, okay. If you have a TE, okay, temperatures profile, then you have this XI, TI plus XJ, TJ, or you have any psi, okay, any parameters, then you have SI, psi I, sorry, I, plus SJ, J. All right. Then if you look into this, now we are, of course, we are interested on the deformations, right? So our deformation in the shape, in terms of linear shape functions, will be SI UI plus SJ UJ. Okay, so that is what we have here. Okay, then if rearrange it in terms of metrics, will be like this. Okay, then we have our shape functions in so-called global coordinates, will be the YJ. Here is related to y, not x. Then your x all replaced by y, yj minus y over l, y minus yi over l. So that gives us the two shape functions in global coordinates. Right. So in the local coordinates, of course, you have also learned before si equals to this y equals to from yi, okay, plus y. From this node I plus y itself is your so-called y. This is so-called y. Then end up you will have this y minus 1 minus y over l and y over l. So it's similar like what we have seen just now, 1 minus x over l, 1 minus sorry, this x over l itself. Okay, so this is similar, okay, but then just now we are looking into horizontal, okay. Then horizontal so-called coordinates. Now we are in a vertical, so we are using y in this case, vertical coordinates, vertical so-called steel columns. Right, so that is where we have our shape function coming in. So this I think is SJ, not SI. Some typo here. Right, so making use of the and we use the energy formulation again. I mean, again, here we are finding minimum total potential energy, okay, to generate the stiffness matrix and the loading matrix under load under axial loading. So it is basically making use of the strain energies and also potential energy. So from the strain energy, the formula is what we call in one element is lambda. Okay, is governed by this stress multiplied with strain divided by 2. Okay, then if you remember that your stress, or what we call your Young's modulus here is modulus of elasticity. Here is stress over strain. Then our stress equals to E epsilon, which is our strains, right? So here will become E epsilon square divided by 2, right? So the total potential energies in this case is basically the difference of the total strain energy and the work done by an external force. Okay, so if we go back to our introduction, we have introduced you this pi. Okay, is our total potential energy. Is basically you sum up all your so-called strain energies, okay, and the work done by the external force. Okay, that is the difference lah. You get the difference between this sum of your strain energy and the work done by the external force, that it will give us a potential energy. So if I want to find the minimum total potential energy, then we have to find the derivative of this particular equations. Let's say this total potential energy equations lah. So we want to find minimum total potential energy, then we find the derivative of it with respect to u. Okay, what we call here is our deformations. Then we will get this formula, and we know that minimum total potential energy in this case is 0. So NF we have this positive formula. If you still remember that will give us K, okay, then U later on minus our F equal to 0. Okay, or we have more familiar if K Q equals to F. Okay, so that is what we have got previously. So back to that, okay, we have our so-called shape functions or our so-called deflections, okay, of one element in terms of its shape function is u. Okay, element is si ui plus sj uj, right? So our si just now we have determined in local coordinates is y1 minus y over l, and sj is y over l in this case, right? And we know that the strain itself is equivalent to our du dy. Okay, basically if you look into this, our strain itself is basically this particular dy basically is the change of our strain is so-called delta L over L, right? So here is our du dy in this case. Okay, so if we can find these strains, we find the derivative of our these strain equations. Okay, so-called deformation equations. Then we can find the strains. Okay, so du dy. Okay, we have the basically is d. Our u is s I ui plus sj uj and over dy itself. Right? Okay, over y itself. With respect to differentiate with respect to y itself. Then we have our strains. Okay, so substitute in I mean our si 1 minus y y 1 minus y over L, right? Then plus y over L uj. All right. Let me find something to show you. All right. So in this particular case, then we have our dy, right? So we have the first part here, dy here is basically 1 over L ui negative plus 1 over L uj. Okay, so our strain here, which is the du dy here, is basically equivalent to u negative ui plus uj over L. Okay, so substitute this thing, okay, into our strain energy equations. Strain energy for arbitrary elements, lambda, which is just now we have defined E epsilon square, which is our strain energy, strain, okay, square divided by 2. Then we have and the integration, and then we have this so-called strain square is basically U is this uj minus ui over L square. Then we have uj square plus I square minus 2uj ui, okay, divide by L square, right? Then of course over V itself, then we have integrate, then we have our E, okay, epsilon square over 2V, okay? Then this V is basically you have this coming here, coming down here, we have this E equals epsilon square over 2 AL, right? So substitute, okay, this epsilon square with this, then it will give us here is AE over 2L multiplied with uj square plus ui square minus 2uj ui. All right. So that basically gives us our strain energy equations, total strain energy equations. So to find the minimum, okay, minimum strain, so-called strain energy, then we basically we minimize it or we differentiate it with respect to we find the derivative with respect to the u. Okay, like what we have discussed just now at the beginning, right? We want to find the minimum total potential energy. So this is what we have to do, right? We minimize it. So in this case, what we have here will be sorry, here, right? So to find our del lambda, okay, of elements, okay, of strain energy with respect to the ui itself, then looking into this formula itself, AE over 2L, sorry, let me change this itself, okay, then we have our AE 2L, right? Then with respect to UI, so we have these two UI minus 2UJ, okay? Then it will give us this AE over L UI minus UJ. So that gives us the first parts or the first so-called nodes strain energies. Then the second one, with respect to UJ itself, then we have this AE over 2L. Then UJ is here, 2UJ minus 2UI. Okay, so that will give us AE over L UJ minus UI. Then if you rearrange it in terms of matrix forms, okay, del lambda, del ui, del lambda, del uj is actually our so-called here we have this, right? AE over L, AE over L ui minus uj. So we have this AE over L ui minus uj, okay? Then we have our AE over L uj minus ui. So in the case of we rearrange it in terms of a stiffness matrix, matrix form ui uj, then probably here will be my AE over L 1 minus 1 minus 1 1. Okay, so that basically gives us our stiffness metric, if you still remember. So okay, so it's similar with our stiffness metrics of that particular element itself. Okay, so our k minus k negative kk is where it comes from, how it comes from here, right? Then we do a minimizing the work done by external force, okay, which is the other parts, which is this parts, this particular part, okay. We have to minimize it with respect to DUI. So if you look into the formula itself, okay, the equation itself is summations of FIUI in this case, right? So here our FIUI, then we have this FIUI plus FJUJ. Okay, so we differentiate or find the derivative with respect to this thing with the UI. Then the second one will be FIUI plus FJUJ del UJ in this case. So that gives us our load matrix, what we call our load matrix is here, which is equivalent to FI FJ. Okay. Right. So then we have, if you rearrange back just now, we have the difference to we have the minimums total potential energy equal to 0, right? So we have basically equals to this, okay, minus this, okay, or minus this. Then we have our so-called k minus k negative k k. Then we have our ui uj, okay, minus our Fj equal to 0. So that gives us our formulas that we from based on this one, based on this minimum total potential energy, then it gives us this. Okay, then to solve the displacement ui uj, then we will know that then we have this so-called k elements, okay, inverse, okay, multiply with our f loads itself, then we can find our u. Right, so looking into these problems, right, consider a 4-story building with a steel columns like this. One column is subject to a loading shown in figures. So you have a 30 level, our so-called 1, 2, 3, level 4, or the floor number 4, we have a 30,000 pound. Then at both sides, right? Then we have a 25,000 pound for the first 3 so-called floors. So we have all these, okay, assuming axial loadings. When we say axial loading is a central, like what we have mentioned, loads. Then vertical displacement of the column at various floor, we have to determine, okay, various displacement, okay, meaning our U1, this is our U2, this is our U3, U4, U5. Okay, so we are asked to determine this U1, U2, U3, U4, U5. Okay, subjected to a loads that as you have seen here. So our F here, so you could have find from here you have we can put it into matrix. From here is U1 is 0, then we have a 50,000. The second U3 F3 is 50,000. Then F4 is 50,000. Okay. Then we have F6, F5 is 60,000. Okay. So if you are assuming going down is going up is positive, then coming down here is negative. So all are going down, coming negative. So we want to determine why is this. So we have the loads matrix. Okay, we need to determine our K G global. Then we can find our U1, U2, U3 until U5. Right? Then we also have to find part B, the stress in each portion of the columns. Okay, so we know that our stress itself, stress, okay, equals to E multiplied with strains. Okay, and our strain itself, we know that is for one element we have this Uj minus Ui, okay, divided by L. Right? So we can also find, if we have find Uj, if we find all this information with the Young modulus, with the length of the column itself, then we can find the length of the column in each element itself. Then we can find the stress developed at any elements. Okay, any element at here, at here, at here. So we look into this. So again, I mean, it's the same, the stiffness matrix that we have determined, just formulate just now is for one element is AEOL 1 minus 1 minus negative 1, 1. Okay, so that is the stiffness matrix of one element. All right, so if you look into that, okay, here we have this is my element 1. Okay, this is my element 2, this is my element 3, this is my element 4. So 4 elements, 5 nodes. 4 elements, 5 nodes. Right? 4 element, 5 nodes. Then if you see that the stiffness, because the length is, I mean, our stiffness K equals to A E over L, right? Right. So A mean the area is uniform, so okay, same, okay, along the elements. Then the L is also the same, 15. For each element, 15 fits. Okay, 15 fits is same, right? So A, E is same, A is same, L is same. So our stiffness, I can say that for each element is same. So here we have our K1 equals to element 1 equals to K2, K3, and K4 in this case. All four elements having the same stiffness matrix. Okay. So here we have our stiffness matrix AE over L, 1, -1, -1, 1. Then we have our A area is 39. Okay, area is 39.7 inch square. Then we have our E is 29 power of 10, 10 power of 6. Okay, power per inch square. Then we have 15 feet. Okay, 1 feet is 12 inch. Then we have 15 times 12. Here is 15 times 12. Here we have 180. Okay, so 180 at here. Then we find our stiffness. Okay, here our stiffness matrix for each element are same. So okay, then we have total. We have this 6.396 10 power 6. So you see the basic steps. Still remember pre-processing phase, we have the elements equations. Okay, we have that already. Then we construct the stiffness matrix. Then we develop the equation for the elements. We assemble them, right? So assembling again is the same lah, like what we have discussed. Under axial loading, okay. So this is our first matrix. First element, this is the second element, this is the third element, this is the fourth element. Okay, this is your KE1, okay, this is E2, this is E3, this is E4. Right, so end up, because we have 5 nodes, then we have this 5 times 5 matrix. Loads, as mentioned to you, we have determined also F1 until F5, right? 0, 5, 50,000, 50,000, 50,000, and 60,000, and negative is going down, right? So we can construct what we call the full equation, which is K G global U equals to F, right? So that gives us this, okay, and we can start to apply a boundary, okay, boundary so-called equation, boundary conditions, okay, and we know that the node 1, what we call the bottoms is fixed here, right? So U1 will be 0. So we applying U1 equals to 0, then this become basically can become 0 this become 1, okay, U1, okay, multiply with U1 equal to 0, right? So that solve it. Then this this -1 multiplied with U1 have to also become 0. So we at the end, we do not need to consider all the first so-called column in this case. And 5 times 5 matrix now become 4 times 4 matrix now. Okay, so we have 4 times 4 matrix multiplied with okay, U2 until U5 is 4 times 1 matrix, so equals to 4 times 1 matrix, right? So then we can solve using what you have learned, solve solutions. Okay, solving this system of algebraic equations simultaneously. So you can use your direct methods, Gauss elimination methods. You can use, if you have manually, then you use Gauss elimination methods, or you use what we call your LU decomposition methods. Or if you have, you can find the inverse matrix, okay? Then you can find, you can use the inverse matrix methods. Or you have MATLAB access, you have Excel, then probably you can make use of the software to solve it, right? So you get the solution is U1, U2, U3, U4, U5 equals to this. All right. Then, sorry?
I have a question. Sorry, doctor. So for the solution part, is it up to us to choose whatever method that we want, or you will specify in the exam that which one we need to use?
if regarding your assessment, then it's free. I mean, up to you. But a lot of I think for my previous sessions, I allow you all to use the software, MATLAB or Excel. You can use it. Okay, and that's why I need you to have this remote access to our labs computer. They have this MATLAB, Excel, everything there. So if you are familiar with MATLAB, then you use MATLAB to solve it. Okay, so in that case, usually it will involve more than three times three matrix or it will be higher order matrix. Then probably you need software. So if my question is just 2 times 2, then probably you do not need the software. You can I would say you have to manual calculate it or using the Gauss elimination method or what. But usually it's more than that. Okay, then I will allow you to use the software. Okay, computation for the computation. I mean, you can have MATLAB, you can have Excel. So it's allowed. Okay, my previous session all are allowed. I mean, they were allowed to use all this software for the computation. Right.
Okay, thanks, Doctor.
So not to worry. Okay, so if you that's why I cover a bit on how to use that MATLAB and Excel, so you basically familiarize with it. And also we have the tutorial questions that basically questions on how to solve this matrix using different types of methods, where if you can try it, then probably you are familiar with it. So the important for me is not the solution. We will leave it for the software to solve it. The important for me part is how to construct this global equations. Okay, Ku equals to F. Okay, and how to apply your boundary and nodes correctly. Okay, that part I think you have to take notes lah. Okay, then if you can solve it, you have U1, U2, U3, U4, U5, then we can find our stress. Okay, here is stress on each element. So element 1, of course, you are measuring, you are minusing your U2 sorry. You are getting the stress one, you are getting U2 minus U1 over L, right? So that you get this. For stress 2, you have U3 minus U2 over L, right? Then stress at element 3 equals to U4 minus U3 over L. 4 equals to U5 minus U4 over L. Right, so that is where you find your stress, okay, in each members or each elements, right? So next we proceed with let's say, okay, now we have these solutions. Okay, we have this solution that we have solve it using let's say we use MATLAB just now to solve it, right? Then we are asked to find we are interested to know, okay, the deflection at point A, which is at here, okay, 10 feet from the ground, and also B, point B, which is 8 feet from the tops, right? Which is a total of here from the ground will be 60 minus 8 lah, right? So we want to determine the deflections, okay, at each point, meaning at here, okay, at here, what is the deflection at here, okay, in verticals, then here, at here, what is the deflection at this particular point, right? So again, we make use of the shape functions that we have discussed, right? So if you have, I thought I shared here. Wait, so we look back into here. If we look back into here, then we know that our y is 10 feet, right? So if we are making use of our so-called global coordinates, then our y here is 10 feet. So that is happen at element 1, okay, and which is between node 1 and node 2 in this case. So we are looking into this particular, okay, 2 nodes and making use of the linear functions y2 minus y over L, which is our Si, okay, or S1. This is our S2 in this case. Then we can actually determine our so-called U. So we have a Y is 10 feet, and we know that our Y1 is 0, Y2 is 15 feet, right? So here, substitute everything in. We have the U1 equal to 0, U2 equals to negative 0.03283. Then we can approximate, okay, our U at so-called 10 feet, okay, at Y equal to 10 feet. We get this. Then the next one will be at B. Point B is 8 feet, total of 60 feet. So from our global coordinates, I mean, here will be 0 at here, right? Our origin. Then here is 52 feet. So our Y now is 52. Happen at where? Happen at element number 4. Okay, happen at element number 4, which is node 4 and 5, right? Happen at node element number 4. So we are looking into this node 4 and node 5, right? Then we have our, again, our we are looking into node 4 and node 5, right? So we have node 4, or Y4 is here, and Y4 here we have, Y4 we have 45, Y5 is 50, right? 15, 15, 15, 45 is at Y4, right? Then Y5 is 60. So Y4 is 45 feet, Y5 is 60 feet, right? And we have U4, U5 equals to what we have here, negative 0.075, negative 0.07504, negative 0.08442. Then again, substitute into our so-called shape functions. Okay, U4 equals to S4 U4 plus S5 U5. Then we can solve it and we get our so-called U when Y equals to 52 feet. Okay, our global coordinate Y equals to 52 feet. So it fall, of course, in between this negative 0.057504 and negative 0.08442 right? So that is about axial members, right?